Hello viewers, welcome back to our channel. In the last lecture of this series, we discussed exponential functions of complex quantity and we learned that how to represent exponential functions of complex number. So in this lecture, we will discuss circular function of complex quantities just as sine of a complex number, cos of a complex number and tangent of a complex number, and we will give their representation when the argument is a complex number. Okay, next we will extend all these definition to prove Euler's theorem, and next we will discuss DeMoivre theorem in this new setting of complex quantities, and after that we will discuss the periodicity of these functions of complex quantities such as sine z, cos z and tangent z. We will discuss periodicity of these functions. After that we will extend all results we have done in case of real numbers. We will extend all formulas of trigonometric function for complex numbers. So this is the layout of today's lecture. So let's start the today's lecture. So student, we know that if x is a real number, then you can write e raised to power iota x as cos x plus iota sin x. Similarly, you can write e raised to power minus iota x is equal to cos x minus iota sin x. Now if we add left hand side and right hand side, then what we have, e raised to power iota x plus e raised to power we get 2 times cos x. It means from here we can give the representation of cos of a real number x in terms of e raised to power iota x plus e raised to power minus iota x divided by 2. So this is the representation of cos of a real number. Okay, now we will extend this definition as cos of a complex number z as e raised to power iota z plus e raised to power minus iota z divided by 2. So what you get from this expansion, right hand side, if you expand this right hand side, whatever you get, that is represented as cos z. Okay, similarly, if you subtract these two equations, then what you have, sine of x is equal to e raised to power iota x minus e raised to power minus iota x divided by 2 iota. So this is the representation of sine of a real variable x. Okay, but we can extend this as, for complex number, sine z is equal to e raised to power iota z minus e raised to power minus iota z divided by 2 iota, where z is a complex number. So again, using this representation, we can extend this to sine of a complex number. So we know the expansion of e raised to power iota x, and we know the expansion of e raised to power minus iota x for every real number x, and similarly we can expand e raised to power iota z and e raised to power minus iota z. So knowing the expansion of these, we can get the formula for cos z and sin z. So this is the representation of trigonometric circular functions for complex variable. Similarly, you can use this to find out tangent of a complex number. So just like as divide sin z by cos z. Sin z by cos z, then you have e raised to power iota z minus e raised to power minus iota z 2 iota e raised to power iota z plus e raised to power minus iota z. So this is the definition of into 2 here, so you get cancel 2 this one. Okay, so what we have, e raised to power iota z minus e raised to power minus iota z divided by e raised to power iota z plus e raised to power minus iota z and iota here. Okay, similarly you can find out the representation of cotangent z. Similarly, you can find out the representation of cosecant z and secant z. Okay, so but these are the basic formulas for circular function of complex variables. Now we move to the second part of today's lecture, that is Euler Theorem for a complex variable z. We know that if x is a real number, then e raised to power iota x is cos x plus iota sin x, and similarly e raised to power minus iota x is equal to cos x minus iota sin x. So in the last step we have find the representation of cos x when x is a real number, that cos of e raised to power iota x plus e raised to power minus iota x by 2. Similarly, you can find the representation of sin x as e raised to power iota x minus e raised to power minus iota x by 2 iota. All these are the representation when x is real. Then we have extended this as cos z for a complex number e raised to power iota z plus e raised to power minus iota z by 2, and we and sine of z as e raised to power iota z minus e raised to power minus iota z by 2 iota. So these are the representation of sine and cos of a complex number. From here we can find that if we add cos z plus iota times sin z, what we get? We get e raised to power iota z plus e raised to power minus iota z by 2 plus iota times sin z is e raised to power iota z minus e raised to power minus iota z by 2 iota. You can get, you can cancel iota with iota and then add what you have, e raised to power iota z. So this is Euler theorem in case of when z is a complex number. So this is the Euler theorem when z is a complex number, and this is Euler theorem when x is a real number. So it means if we replace a real number by a complex number, then Euler theorem still holds for a complex quantity. Now moving to the third part, we extend the statement of DeMoivre's theorem for a complex number. Okay, so what we have seen in Euler theorem, if z is a complex number, then e raised to power iota z is equal to cos z plus iota sin z. So this is the extension of Euler theorem for a complex number. Okay, now we will establish the DeMoivre theorem for complex number. It means if you take n as a power, then you can move n inside the angle as. Okay, so if you know that the portion in the bracket is e raised to power iota z, because cos z is e raised to power iota z is cos z plus iota sin z, and n outside. Okay, so you can write this as e raised to power iota nz, and this way you can write this as cos of nz plus iota sin of nz. So this is the DeMoivre's theorem for a complex quantity, and you have seen that if n is in power, then you can move n as an angle of cos. Okay, so this is the extension of DeMoivre's theorem for a complex number. So students, now we move to our next topic of the day, periodicity of sin z, cos z and tangent z. First we prove that sin z is a periodic function of period 2k pi. It means if we add 2k pi to z, then we again get the same value. Okay, so this is our claim. It means the sine z is a periodic function of period 2k pi. So you know that what is the expression for sine z is e raised to power iota z minus e raised to power minus iota z by 2 iota. Now replace z by z plus 2k pi. So what you get? You get e raised to power iota z plus 2k pi minus e raised to power minus iota z plus 2k pi divided by 2 iota. Now separate the numerator as e raised to power iota z times e raised to power iota 2k pi. Similarly, minus e raised to power minus iota z times e raised to power minus iota 2k pi divided by 2 iota. Okay, and this will be e raised to power iota z minus e raised to power minus iota z by 2 iota, because e raised to power iota times 2k pi is nothing but cos 2k pi plus iota sine 2k pi, and you know that cos 2k pi is 1 and sine 2k pi is 0. So it means e raised to power iota times 2k pi is 1. Okay, so this quantity is 1, this quantity is 1, so we are left with this expression. So it means, what can you say now? Z plus 2k pi will give you the value same as sine z. So it means sine is a periodic function of period 2k pi. Similarly, you can show that cos z is also a periodic function of period 2k pi. Similarly, cos is again a periodic function of period 2k pi. You can use the same argument to establish this result. Okay, in this sequence we now show that the tangent z is a periodic function of period n pi. Now we show that tangent of z plus n pi or k pi, you can write, is same as tangent z. Now first we apply the expression for the tangent of a complex number. So what is the expression for tangent of a complex number? E raised to power iota z minus e raised to power minus iota z divided by e raised to power iota z plus e raised to power minus iota z, and this one by iota. Okay, now replace z to z plus n pi. So tangent z plus n pi will be 1 by iota e raised to power iota z plus n pi minus e raised to power minus iota z plus n pi. Similarly, in the numerator, you can write e raised to power iota z plus n pi plus e raised to power minus iota z plus n pi. Now simplify this as tangent of z plus n pi is 1 over iota e raised to power iota z into e raised to power iota n pi minus e raised to power minus iota z into e raised to power minus iota n pi. Similarly, you can do the same thing in the denominator also. E raised to power iota z into e raised to power iota n pi mine plus e raised to power minus iota z into e raised to power minus iota n pi. Now, what you can do, you can write this expression again, 1 by iota e raised to power iota z times e raised to power iota n pi minus e raised to power minus iota z times 1 over e raised to power iota n pi. Similarly, in the denominator, e raised to power iota z e raised to power iota n pi plus e raised to power minus iota z into 1 over e raised to power iota n pi. Now take the LCM. So if you take LCM, then what you get, 1 by iota e raised to power iota z into e raised to power iota 2n pi minus e raised to power minus iota z divided by e raised to power iota z into e raised to power iota 2n pi plus e raised to power minus iota z. Okay, and you know that what is this? This is nothing but 1. Okay, so this can be written as 1 over iota e raised to power iota z minus e raised to power minus iota z divided by e raised to power iota z plus e raised to power minus iota z, and this is nothing but this is tangent of z. So what you have shown? You have shown that tangent of a complex number is a periodic function of period n pi. Okay, so this completes the periodicity of circular function of complex variables. Now we move our lecture in the fourth part of this session. Okay, so in this portion we will discuss our trigonometric formulas which we have learned in lower classes. Now you can extend all these formulas for complex quantities also. Let me do a couple of for you. First one is, you know that sine square theta plus cos square theta is 1 if theta is a real number. So you can extend this for complex number also. Sine square z plus cos square z is also 1. And if you want to prove this, just you have to stick on the basic definition of sine z. What is sine z? E raised to power iota z minus e raised to power minus iota z by 2 iota. And similarly, what is cos z? Cos z is e raised to power iota z plus e raised to power minus iota z by 2. It means to establish every trigonometric identity for complex quantities, you have to focus on these two formula only. Okay, and you will get the desired result. For example, if we substitute the value of sine z here, then what you get, e raised to power iota z minus e raised to power minus iota z by 2 iota square. Similarly, if you replace the value of cos z here, e raised to power iota z plus e raised to power minus iota z by 2 the whole square. Now open these squares. So first, e raised to power iota 2z plus e raised to power minus iota 2z minus 2 times e raised to power iota z into e raised to power minus iota z. And in the denominator of the first factor, what you have, minus 4, because 2 iota square will be minus 4. Similarly, you can expand the second expression as e raised to power iota 2z plus e raised to power minus iota 2z plus 2 times e raised to power iota z into e raised to power minus iota z divided by 4. Okay, now collect minus 1 by 4 outside. So what you get, e raised to power iota 2z plus e raised to power minus iota 2z minus 2, because these two terms are inverse of each other, so you will get product 1 here. Okay, so plus, oh sorry, and let me correct, this will be minus because we have taken minus 1 by 4 outside, so this will be minus e raised to power iota 2z minus e raised to power minus iota 2z, and then minus 2. So what you can do now, you can cancel this quantity with this and this quantity with this, and you are left with 1. So what we have established that sine square z plus cos square z is equal to 1 holds for complex number also. Similarly, you can say that sine of 2z is equal to 2 sine z cos z. We know this expression for the case when z is a real number, because we know that sine 2 theta is 2 sine theta and cos theta. Okay, this result holds when theta is a real number. Now we will establish this result for complex number. Okay, again what you have to do, you have to fix on the definition of sin z and cos z and start from the right hand side. Okay, so if we start from the right hand side, 2 sin z cos z is 2, put the value of sin z, e raised to power iota z minus e raised to power minus iota z by 2 iota, and then put the value of cos z, e raised to power iota z plus e raised to power minus iota z by 2. Okay, now open the expression. You can cancel 2 with this 2. Okay, so what we are left with 1 by 2 into iota. Okay, now open the bracket, e raised to power iota z multiplied by e raised to power iota z, e raised to power iota 2z. Okay, now this multiplied by this get 1, so 1. Now multiply this by this quantity, so what you get minus 1, and then multiply this quantity by this and you get minus e raised to power minus iota 2z. So you can cancel 1 with 1 and you are left with 1 over iota e raised to power iota 2z minus e raised to power minus iota 2z by 2, and this is nothing but it is the formula for sine of 2z, because if you replace z, if you replace 2z in place of z, you will get this formula. Okay, so similarly you can you can establish other trigonometric identities for complex number. Let me mention without proof some trigonometric identities. So you can show that sine of z1 plus z2 is sin z1 cos z2 plus cos z1 sin z2, and similarly for the negative one you can prove this. But you have to do, you have to put the value of sine cos as we have did in first part. Okay, similarly you can show that cos of z1 plus z2 is cos z1 cos z2 minus sin z1 sin z2, and if you have the difference here minus, then you can replace this minus by plus. Okay, there are some more identities you can prove, that cos of 2z is equal to cos square z minus sin square z. Similarly, you can prove that sine of 3z is equal to 3 sine z minus 4 sine cube z. So you can prove, you can extend any other trigonometric identity as we have done in the lower classes for real variable. You can extend those results for complex variable, but the only thing you have to fix, that you have to stuck on this fact that sine z is e raised to power iota z minus e raised to power minus iota z by 2 iota. Only use these simple results and you will get through the proof of all these expressions. Okay, so these are our basic formulas which will help you to prove all these identity. Okay students, so hope you have learned a lot from this lecture. If you like the contents of our channel, please share and subscribe. Thank you.